Okay, so good morning and happy Monday to you. I am sorry that I missed class today and I am sorry that I said it last minute. So I am recording this for the thermodynamics class of what is it now? Fall 2019. So I just want to summarize what we've done so far and finish chapter one because chapter one is just an introduction. So there probably won't be any recommended problems from chapter one. I'm going to change some things a little bit. But we need this background before we start the conservation of energy. All right, so we started. I'm going to follow my notes, and then when we get to the new stuff from chapter one, I'm going to send you guys the notes. So that should be attached to an email that I sent you. So we said that in thermodynamics, we're working with energy. We said that. And energy is the ability to cause change. So we will be working with transfer of energy and transformation of energy. So we know that energy is not created and energy is not destroyed. So we said that we will cover the first law and the second law in this class, and everything will be a bit superficial, and that's how it is in thermodynamics, especially if it's one semester. Then, when we want to talk about heat transfer, for example, and we want to go deep into that, then there's a heat transfer course, so you would do that later on. So we said that units are very important. We don't want to ignore them. When we get to conservation of energy, we will see plenty of examples on this. Like, we don't want to ignore the units. Units are important and sometimes they are helpful in order for us to determine if we solved the problem correctly. Okay? We said that we will only be working with the international system of units, so that's convenient for us. So let's see what else. After that, we talked about systems. We said that we will see two different kinds of systems in this class: open systems and closed systems. Just a comment you can write down if you want. Another way to call a closed system is control mass. Another way to call an open system is control volume. So you will see that in heat transfer fluids later on. You will see those names. A closed system is a fixed amount of mass. There's no mass crossing the boundary, so we know that. An open system is a region in space, and there is mass, or mass may cross the boundary. So then the equations are more difficult, and you'll get to that later on as well. After that, we said we have our system. It doesn't matter what class we're taking. We have our system. It's open. It's closed. What's happening to it? What are we doing to it? We need to know its properties before we analyze. If there's a change in a property, what happened to it, why is it useful to us, and so on. So we have intensive versus extensive properties. We saw the example with the eraser. We said intensive examples of those are pressure and temperature, extensive mass and volume. But a lot of the extensive properties, such as volume and energy, we use them a lot. So we divide by mass, we eliminate that dependence on mass. And how many minutes have I? 3 minutes. And they are called specific properties, such as specific energy or specific volume. We represent them with lowercase, same symbol as the extensive property, but lowercase instead of uppercase. Okay? So I'm just going over, this is a review of what we did in class already. After that, we mentioned, let's see, 1.5, we didn't go over it, so we moved on to 1.6. So you're following your textbook. We said state and equilibrium. State is the condition of the system fixed by its properties. So is it a gas? Is it a liquid? Is it a solid? Is it in saturation? Is it an ideal gas? What is it? So that will depend on its properties. So we will see that very soon. If we have the minimum amount of properties that we need, we can determine what we have, okay? So then we saw equilibrium, no unbalanced potential within the system. So we don't have more molecules on one side of it and fewer molecules on the other side. That will cause the molecules to move in one direction, or the temperature, I think that's the example that we saw, different on one side and like one value here, a higher value here, and then we'll have heat transfer within our system. So we would have an unbalanced potential. So that would not be in thermal equilibrium. So whenever we can make those assumptions in this class, I'll let you guys know. So that was it for our first week. And then after that, all right, this next page, this new page, I am going to attach on an email. So you guys should see this as, I don't know how many pages it'll be, but you should take a look, all right, and maybe write it down if you want. Just remember that all of this is still an introduction. The next section, processes and cycles, okay? So over there, let's see. If you said last section for the day, you may ignore that because obviously we didn't get to that last time. But a process is when we have different states, all right? So we have a system. It starts at one state, so I start over here. We're over here, all right? With a certain mass, certain temperature, certain pressure, and then I finish all the way over here, or it could be the same place, but I have at least one property changed, okay? So there is a new state. So that means that we undergo a process, okay? Now, there's a question over there. Are the following systems undergoing processes? Question number 1, it says closed system, mass is changing. So we said the property changed, so I have a process. But, a closed system, the mass is supposed to be constant. So that we cannot say, oh, it's undergoing a process. We have to figure out, did I calculate the mass in an incorrect way, or is this an open system before I move on? And like I say there, people are not trying to trick you, but you have to figure out what's going on. It's your responsibility before moving on with the analysis, okay? Second question, it says temperature is going from 100 to 120 degrees Celsius. Is that a process? Yes, all right? Temperature is changing. So a few processes that we will see in this class: isothermal, constant temperature; isobaric, constant pressure; isometric, constant volume. If you don't remember that on your exam, or you don't have that on your notes, and you see the word isobaric on your exam and you freak out or you don't remember what it is, you may ask me. It's like, hey, please come here. What does this mean? And then we'll figure it out together, okay? Now, the very next definition that we see over there, a cycle, is a series of processes. So it's more than one. And they begin and they end at the same state, all right? So I start in my office and I walk around campus and then I come back to my office, all right? So I end at the same place. Now, it's not a very good example because maybe I do not have the same amount of energy or the same amount of mass when I end there. But, all right, in a thermodynamic cycle, we begin and we end at the same state. It means that if I began at 1 atmosphere, 100 degrees Celsius, 1 kilogram, not me, my system, and energy of 100 kilojoules per kilogram, specific energy, then if that's my initial state, it doesn't matter how many processes I have, that will be my final state. And this is very important, all right, for your exam, for future chapters, to remember what a cycle is. So we're not talking about a power cycle yet, or a heat pump, or refrigeration cycle. Just in general, a cycle begins and ends at the same state. So, question over there. It says a cycle has 3 processes. The first one is expansion, all right, at constant pressure. The second one is at constant volume. So again, first one, expansion at constant pressure. The second one is a constant volume. So can the third and final process be at constant volume? That is the question. So the answer is no, because we have to return to its initial volume, okay? So if you have any questions, please pause, all right, and ask me about it. Now, the next page that I'm sending to you, there are a lot of comments there. Let me see. I'm going to cover up some of the comments because it's just mostly me talking to myself. That's why I don't send you guys my notes. So temperature is related to the kinetic energy of the molecules of a system, is what it says over there. It means that it has to do with how fast those molecules are moving within your system. Temperature is related to that, okay? However, in this class, we don't analyze that microscopic behavior, but you will analyze it later, okay? So the temperature of my system, is it hot or is it cold? Because this is relative. It has to do with how the molecules are moving. Not just how they're moving, how fast they're moving, okay? Now, there are 2 different kinds of scales. There's a 2-point scale, such as Celsius and Fahrenheit, and that is developed using the properties of a substance. But then we have the thermodynamic scales, or absolute scales, and you should write this down, such as Kelvin and Rankine scale. We'll use Kelvin because that's one for International System of Units, that they do not depend, we do not develop that scale using the properties of water the way we do for Celsius and Fahrenheit, all right? 0 Kelvin and 0 degrees Rankine is the lowest possible temperature, and in order for us to develop the rest of it, we need to use the second law, which is later on. So again, for temperature, we know that we have degrees Celsius, we know that we have Kelvin. for International System of Units. One of them is a 2-point scale. One of them is the absolute scale, which is more useful to us when we get to equations such as ideal gas equation of state. And the conversion between the two, just in case you don't know it, we have degrees Celsius plus 273.15, or we can just say plus 273. You don't have to include the 0.15 to go from Celsius to Kelvin, all right? So something that I tend to ask is, what about the delta temperature, okay? If we have delta T in degrees Celsius, how does it compare to delta T in Kelvin? So this is important for your exam. Sometimes it's there, okay? So if I go from 10 degrees Celsius to 20 degrees Celsius, that delta is 10, right? Degrees Celsius. So what happens if I have it in Kelvin? 10 is 283 Kelvin. 20 is 293 Kelvin. So that delta in Kelvin is 10 Kelvin. So delta T in degrees Celsius is equal to delta T in Kelvin when we have a process. All right, so I want you guys to remember that. All right, so again, if there are any questions, please pause this and talk to me, all right? Send me an email, send me a text. I'm a little sick, it's complicated, but I can still answer your questions. The very next section is pressure. Now, in the past, I have talked about absolute pressure, atmospheric pressure, gauge, vacuum pressure, barometers, manometers. So you would see all of that if you study the old exams. However, okay, this is the first time that I will skip this, all right? And this will limit the amount of questions that I can ask on your first exam. But, all right, there's a reason for this, all right? If I want to talk about any of this, like vacuum pressure, gauge pressure, anything like this, and I want to test you on it, I'll cover this when it's relevant later on, okay? So for pressure, we can write this down if you want for 1.9. If you are interested in learning any of this, please come see me. We can talk about it. We can talk about gauge and vacuum pressure and absolute and atmospheric pressure and all of that. But for now, I just want you to remember, this is force divided by area. They're perpendicular to each other, okay? And we're not going to complicate this too much. When you get to fluids, you'll talk about normal and shear stresses and things like that. But for us, we'll say we are working with the absolute pressure, all right, of a system. So that's all I want you guys to know right now. The absolute pressure of a system, the one that we will work with, is always positive, all right? It means that we measure that with respect to absolute vacuum. It means that when we use PV equals to MRT for ideal gases, the pressure that you have in that equation is positive, right? That's it. That's all I want you guys to know about pressure right now. It doesn't mean that the rest is not important. It just means that if we're going to use that later on, like manometer, change in pressure, pressure below atmospheric pressure, if we use that later on, I'll cover that then, okay? So let's see if there's anything else in chapter 1. That's it. That's it. So I know this is really short. You're like, but I mean, this should be similar to a 15-minute class. But no. So again, the introduction, all right? Introduction is that energy, ability to cause change, okay? We're going to cover that. We're going to talk about kinetic potential, internal energy, and enthalpy, and other terms that are related to energy. Before we do that, we need to learn the basics. We'll learn conservation of energy. We'll apply conservation of energy to our different kinds of systems. Closed system, which is the easier of the two. Open systems, not that easy, still pretty easy. We'll apply that to them. Our governing equations, conservation of energy, conservation of mass, second law later on. When we have these equations, the properties will show up in these equations, all right? Those characteristics. We'll have intensive properties, we'll have extensive properties. We need to know how to calculate them. We need to know how to retrieve them, all right? We need to know how many we need to define the state, and so on. So all of these terms will show up later. So it was just in order for us to see them for the first time, all right? So we're familiar with them, okay? So for chapter 1, there are no recommended problems. So if you have any questions or you're curious, because it's great to be curious, and you want to learn more about any of these topics, please call me on the phone or text me, send me an email, or read the textbook. You don't have to read it. You can just contact me, all right? And we can talk more about that. So that's it. And I have 7 seconds left. All right. So I'll see you guys later. Take care.